Okay, so let's, in this video, do a couple more problems with non-inertial frames. And the first one I'm going to do is one similar to one you'd have in your textbook. Let's imagine we have a wheel that's rolling with a constant velocity along a straight line here, and let's find what the acceleration of a point on the edge of the wheel would be. Okay. So let's say our wheel has a radius of b, and it's moving with a constant velocity v naught. So of course on the edge of this wheel, this point is moving at this instant of time. It's moving with a velocity v naught, right? But that's with respect to a fixed frame. If you're moving with the frame, so let's make a coordinate system for the rotating frame, which is the wheel. Let's call this the x direction. Let's call straight out the z direction. So that goes like an axis through that wheel. And then of course the y direction. Okay. So yeah, if you look from rest, it looks like that at that instant of time that's going with v naught that way. But if you're moving with this rotating frame, it stays there all the time. So r is bx in the rotating frame. The velocity in the rotating frame is 0. Omega, so the wheel is rotating around this axis, so it's in the z direction. But since this thing is going v naught, you guys know a relationship between the rotational speed and this linear speed here, and it's v naught is omega times the radius, right? So I can rewrite omega as v naught over b. Okay, so our effective force on the point on the edge of the wheel is any real forces. And of course it's stuck to the wheel, so there's some kind of real forces. And then we have the Coriolis force. We have this force, which is sometimes just called the transverse force. And then we have the centrifugal. It's supposed to be an m omega cross r. Okay. Well, we said the velocity in the rotating frame of that point on the wheel is 0. It doesn't think it's moving because its frame is rotating. We're assuming a constant speed, so it'll be a constant omega, so this will go to 0, and we only have the centrifugal force that we have to worry about. So let's look at omega cross r first. So omega is v naught over b, r is b, and then that's in the z direction crossed into r is in the x direction. So z cross x is in the y direction. You can use your right hand, figure that out. So you get that. So then omega cross r is going to be omega is v naught over b. And this was v naught, so I have a v naught squared. Omega is in the z direction, and this was in the y direction. So z cross y, let's see. Is your negative x? I think I did that right. So in the rotating frame, you think that you have, if I have that negative and I have negative up here, it makes it a positive m v naught squared bx. So in the rotating frame, you think you have a force pointing out in the x direction, trying to push you out that way. And you've all felt that. You go around a track in a car or a road and you have a curve, you feel like you're being pushed towards the door, so you feel like there's a force that way. But it becomes because you're in a non inertial frame, you're in a rotating frame. So if you look at the real force, you're going to have the force would be towards the center of the wheel, exactly like you would expect. That's the real force. Okay? Okay, let's do another example. Maybe something rotating too. I know what we'll do. We'll do the famous, let's say we have a merry-go-round here. So the z-axis comes out of the page here. And here's a line along this, and this is rotating around this direction. And let's say you have a bug. And the bug's moving at a constant velocity, v naught, in its frame, going that way. So in the rotating frame. And let's call this, let's see, so that's our x direction. Y direction is this way, so z will be up and out of the page here. So let's bug crawls along a straight line in the rotating frame. With speed v naught. So let's find all the apparent forces on the bug. Okay, so the bug at any one time is at x. He's at a distance x from the origin in the x hat direction in his reference frame. His velocity in his reference frame is v naught x hat. Omega is omega times z hat. Okay, so let's look at the various forces. First of all, this one is 0 because we're assuming omega is constant there. So let's look at the Coriolis force. Omega, and then r is just x. Oh no, I'm sorry, that's not the Coriolis force. The Coriolis force, excuse me, is omega cross v, right? Which is omega v naught, and then we have z hat crossed into x hat. And that's in the y hat direction, so then we get negative 2m omega v naught y hat. So we have that force, and then we have the centrifugal force. Omega cross r. Now we have the r, so that's equal to negative m omega crossed. That's omega, and that's x. And then this is z hat again crossed into x hat, which again is y. So equals negative m omega squared x, and then this is going to be z hat crossed into y, because that's what this is. And that's in the negative x direction, so plus m omega squared x, x hat direction. There we go. We've got the effective forces. So the effective forces on the bug, the force the bug feels, is any real forces, which are like the normal force acting on it, gravity acting on it, friction force between it and the surface. Then we have minus 2m omega v naught in the y hat direction, yes. And then plus m omega squared x in the x hat direction. So there you go. There's now I should make the point that in the bug's reference frame, he's going at a constant velocity. He's going in a constant direction at a constant speed. So in his reference frame, there's no net force. So these should add up to 0. So there's two examples, non-inertial reference frames.